Before we start on the main topic, we have an important announcement to make. After this video, we will be taking a detour from probability theory to cover some essential pre-calculus and calculus topics. And the reason why we are taking this detour is that these topics are essential for understanding the next parts of probability theory, which are based on continuous probability distributions. And to be able to understand these topics, we will need to build a strong foundation in calculus. Here is the curriculum for the pre-calculus and calculus topics that we will be covering in the coming months. Starting with pre-calculus, we will cover topics such as functions and graphs, trigonometry, analytic geometry, sequences and series, and many more. After pre-calculus, we will move on to calculus, where we will cover topics such as limits and continuity, derivatives and their applications, integrals and their applications, differential equations, and many more. These topics are not only essential for understanding probability theory, but also for understanding the concepts in deep learning and machine learning. If you want to really understand how neural networks work, you need to understand these topics in depth. And the amazing part is that the same concepts are not only used in machine learning, but also in physics, engineering, computer graphics, and many more fields. So it is really worth investing your time in learning these topics. So I hope you are as excited as I am to learn these topics. Now let's get back to our main topic of today's video, which is Poisson distribution. The Poisson distribution is a probability distribution that expresses the probability of a given number of events occurring in a fixed interval of time or space. It is named after the French mathematician Siméon Denis Poisson because he introduced it in 1837 while doing research on probability of judgments in criminal and civil matters. Mathematically, the Poisson distribution is defined as follows. Here, Px equals sign k is the probability of k events occurring in a fixed interval of time or space. Lambda is the average number of events. E is Euler's number, which is approximately equal to 2.718, and k is the number of events. Now, let's take a use case to see where Poisson distribution can be applied. Suppose we are trying to analyze the number of viewers' visits per minute on our channel. Historical data show that on average, the channel receives 3 visits per minute. We are asked to find the probability that the channel will receive exactly 5 visits in a minute. To solve this problem, we will use the Poisson distribution formula that we discussed earlier. From the problem statement, we know that lambda equals 3 since the channel receives 3 visits per minute on average, and k equals 5 since we are asked to find the probability of 5 visits per minute. Now we can substitute these values in the Poisson distribution formula to find the probability of 5 visits per minute. After solving the above expression, we get the probability of 5 visits per minute as around 0.1 or 10%. This means that there is a 10% chance that the channel will receive exactly 5 visits in a minute. And that's all for today. I hope you enjoyed this video and are excited to learn about what's coming next. As discussed earlier, we will be covering some essential pre-calculus and calculus topics in the coming months. So stay tuned for that, and as always, thank you for watching.